So in the last few videos, we spent quite a bit of time talking about relative extrema, right? Relative minimum and relative maximum values. And that's where we were just concerned with finding any old high point, any old low point on our function, right? Now we're going to look at a related concept, but a little bit different. It's called absolute extrema. An absolute now is referring to, for instance, the highest of the highs and the lowest of the lows, right? So we don't want to find just any old peak. We want to find the highest peak, or literally the highest point that a function will attain. And similarly, we're not just interested with any old valley. We want the lowest of the low. So we want that lowest point on the graph. And that's why we now refer to these as absolute, right? So let's actually give a definition of both and then look at some graphs to kind of like a qualitative look at this concept and then see again how the derivative can help us answer this particular question, right? So let f of x be a function defined on some interval. Now notice all it's saying is defined. So it doesn't even mean the function doesn't have to be continuous, certainly doesn't have to be differentiable. We just have to make sure that the function is well defined at every point in some interval, right? And let x equals x0 be a number in that interval. So let's say x0 be in this interval. Well, if f of x0 is greater than or equal to f of x for all x values in this interval, right? So for all x in this interval, then this f of x0 is said to be the absolute maximum of f of x on this interval. So then f of x0 is the absolute, or sometimes called global, so absolute or global maximum of f of x over this interval. Right, so notice what the inequality is saying. It's saying that this is a specific number, right? So this is the y value on that corresponds to x equals x0. And it's saying that that y value is greater than or equal to all other y values. Hence, maximum. It's the largest value the function attains. Not just in some, for some values of x, but for all values of x. And this could be the entire real line. When we talk about an interval, it could be the interval from negative infinity to positive infinity. So that's why we refer to it as a global or absolute maximum. And then similarly, if the function value evaluated at that point is less than or equal to all the other function values, right? So again, if this is the lowest value that the function attains, again, this is for all x in this interval, right? Then we say f of x0, so this is the y value now, f of x0 is the absolute or global minimum of f of x over this interval, right? And it's not even saying what type of interval. It could be anything. It could be, like I said, the entire real line. It could be an open interval. It could be a closed interval. It could be semi-open, a semi-closed interval. Lots of different things. So let's get a few pictures drawn so that we can at least visualize what this is saying, right? So let's say, for instance, this is a, so here's my real line, going from negative infinity to positive infinity. And let's say I were to draw a parabola that opens up. And I'm going to put my arrows like this, and we know how we interpret the arrows is that this pattern continues indefinitely. Well, if our graph were to look like this, with arrows indicating that the function is just approaching the heavens, it just keeps getting higher and higher and higher, then this would tell me that there is no absolute maximum. Because if you pick a max, well, I could find another one that could make the parabola go even higher, right? So if you were to pick an x0 to say, oh, here is the max, I could say, nope, I can find another x0 that would give me an even bigger y. So with this sort of pattern, right, we would say that there is no absolute maximum. So no absolute max. However, right here, this is the lowest point that the function attains. So this would be like my x0, and then let me go across here. Whatever that is on my y-axis, that would be f of x0. So the function would have an absolute maximum of this y value, minimum of this y value at this x value. So we would have an absolute minimum at the point x0 comma f of x0, right? So the x value is telling you where the absolute value occurs. So like where along the x-axis are you going to find this extreme point, in this case the minimum. And then the y value tells you what value the max, in this case the minimum, is, right? So the x value gives you the location. In other words, it answers the question where, right? The y value gives you the value of the absolute extrema. In other words, it answers the question how much, how high, how low, right? So where does it occur and what is its value? How much is it? How high is it? Or how low is it, right? So you have some functions, and polynomials are really good examples of this, where you might have one absolute but not the other, right? Then you have some functions that have neither. So for instance, let's say, again, this is my real line. And an example of a function like what I'm about to draw would be something like y equals x cubed. It goes like this. Right, it should be a little flatter in there, but the point of this is that it extends indefinitely as high as you want, and this as you go further to the right, as x goes further to the right, your y value increases. As you go to the left, your y value decreases, and it does so indefinitely. So this idea, so your function goes off to positive infinity this way, negative infinity this way, so there's no way it can attain an absolute maximum or absolute minimum, right? So if a graph were to look like this over the entire real line, or even a portion of the real line, it doesn't even have to be the entire real line, well, what we would say is this function has no absolute minimum nor maximum, right? Okay, so what if our interval isn't infinite, like going from negative infinity to positive infinity? What if it goes from like A to B? Well, even then you can have strange things. So let me show you something where neither endpoint is included, right? So now we're saying that we have an interval A to B. And since the endpoint isn't included, so I could draw something like this, an open circle there, and then I could draw stuff like this, and then there, right? Well, I can look at this and I see where it has some relative maximums, relative minimums, and there's another relative max, there's a relative min, and so forth. But it doesn't have any absolute extrema because the endpoints are not included. There is no like y value that corresponds to that point. So even though you might say it has a limit, it might be approaching this lowest value, but it never attains that value. Similarly here with that open circle, right? It doesn't attain that highest point. So in other words, there is no f of x0 that I could say represents the largest y value on this graph, right? Similarly, there is none that I would say corresponds to the lowest point on this graph, right? So it doesn't have to be where your function goes off to plus or minus infinity. You could have functions like this where you kind of play with the endpoints, either including them or not, and then you get different scenarios. So this scenario, in this scenario, we would say that the function has no absolute min nor max, right? How could I fix it? Well, I could fix it like this. Now, what if I include my endpoints? So I use that kind of square bracket notation, and then let's say A and B. So now I'm going to draw a couple of this form where the interval will be closed and just show you some of the different things that can happen. If I assume that my function is now continuous, right? So for instance, what I could say here, this would be my, so this point right here would be my absolute max. And then this point here would be my absolute min, right? Let's draw a few more so you can see what's going on. So we could see where it could occur. So the highest of the high and the lowest of the low, those could occur at the endpoints of the interval. It doesn't have to though. Take a look at these. All right, so again, let's say we have a closed interval A to B, A to B, right? It could be a situation where my function does something like this, right? Where the absolute max would be right here. Again, identify that highest point, right? Identify that highest point. So this now, whatever that ordered pair is, that would be my absolute maximum. And whatever this low point is, whatever that ordered pair is, it has to have an x and a y, right? Because it's on my function that's nice and continuous. That point would correspond to an absolute minimum, right? But look at where those absolute values occur. They occur at stationary points. They occur where my derivative is 0, right? So at this point here, we have a horizontal tangent, so at that point, our derivative is equal to 0. Similarly, at that point, our derivative is equal to 0. Right? So again, notice where these things could occur. Here's another situation. Same closed interval, continuous function. And let's say it does something like, so let's say it starts here, goes up there, comes back down, stops there, and then goes there, right? Look at that. That's a continuous function, right? Now we know it's not differentiable. We see a couple of sharp corners, but look at what happens. The way I drew it, the the sharp corners happen to correspond to your absolute max right here. So this is your absolute max. And then over here, that is your absolute min, right? So these three pictures, right? Now, pictures aren't proofs. And in fact, the reason I'm doing a lot of these pictures is because the formal proof of the theorem that I'm about to state, it is a deceptively simple theorem, but it's not easy to prove, right? But the whole idea is when you're talking about a continuous function on a closed interval, you have to have some highest point and some lowest point. And they will occur either at endpoints, like here, or at stationary values inside the interval, like here, or finally, the singular values where the derivative doesn't exist. Actually, I shouldn't draw dotted lines there. Let me take those off. Right? So at this point here, we know that f prime does not exist. And similarly here, that sharp corner, right, f prime does not exist. And it turns out for continuous functions, if your interval is closed, meaning you start at one number and at another number, and those two numbers are included, and if you have a continuous function over that interval, then at some point the function has to hit a high value, whether it's at an endpoint or at a singular point or at a stationary point. It has to occur both a max and a min, right? So that guarantee is good. Not only is the existence good, but we know where to check. It is either going to occur at endpoints or at critical values inside the interval. All right. So let's actually state this, and this is called the extreme value theorem, EVT. Right. So this is our theorem, and this is the extreme value theorem, and it's abbreviated EVT. So we have an IVT, intermediate value theorem, from way back when we were doing just continuity. Now that we're doing the extremist stuff, we have an extreme value theorem, and this is what it says. It says if f of x is continuous on a closed interval, and that's key. The interval has to be closed. We saw, for instance, when you go from an interval like negative infinity to positive infinity, there is no guarantee. Even here, where the interval isn't closed, right? There is no guarantee. So if the f of x is continuous on a closed interval, and that's called, actually, I like to, let me use my inequality. So here is the interval, right? And we notice the equal sign that tells us that the endpoints are included. Then, so f of x must attain an absolute maximum and absolute minimum on that interval, right? So on that interval, there has to be a highest of the high and the lowest of a low on that interval. All right, and I'll go ahead and add a little bit more. I'll say, moreover, these absolute extrema, and extrema is just a plural for both, so these absolute, so some people say extrema, some people say extrema, but these absolute extrema must occur either at the endpoints, so it must occur at the endpoints of the interval, or at critical values inside the interval. So, or at critical, I think I misplaced the dot over my I. So at critical values inside the interval, right? So that gives us a nice way of kind of determining where they are. Like, where are the absolute min and max, and what is their value, right? Okay, so let's do an example of this, and as usual, let's start by looking at let's say a polynomial, right? So we'll always like to start with our polynomial. All right, so one is this. So find the absolute extrema, meaning both, right, max and min, of, and here's our function. I use a different variable. Let's use t instead of x. So let's say g of t is equal to 2t cubed plus 3t squared minus 12t plus 4 on the interval, let's say, t between -4 and 2. All right? So absolute extrema, that's where we want to find the highest of the high, the lowest of the low. And we see that the extreme value theorem applies. Why does it apply? 1. Continuous function. We know that polynomials are always continuous. 2. Closed interval, from a number to another number where the endpoints are included. So closed interval. These two things allow us to use our EVT, right? So we know that we have to get an answer, it's just a matter of going through the process. So let me highlight the steps as we go through this example. So the first step will be to find the critical values of this function, right? Because we already have the endpoints, right? So let's say, so step 1, find critical values. Think of how many processes now that we start out by finding the critical values. And by that, you take the derivative, set it equal to 0, and see if we get any numbers, any critical values between -4 and 2. So that's our first step, right? So g prime of t is equal to 6t squared plus 6t minus 12. So we have to ask ourselves those two questions. Where is this derivative equal to 0? And where is this derivative undefined? Well, it's a polynomial, so it's never undefined. but it could be equal to 0. Let's see if we can find the values of t that make it equal to 0. So let's take our 6t squared plus 6t minus 12, set it equal to 0. Let's go ahead and divide through by 6. So if we divide through by 6, we'll have t squared plus t minus 2, and this one factors nicely. It's t plus 2 times t minus 1. So we get two critical numbers, critical values, so t equals negative 2 or t equals 1. And both of these are inside this interval, right? So once we have the critical values, then step 2 now is algebra. Because what we're trying to do is to figure out how high our polynomial is. Like, what is the highest point on the graph of this function? What is the lowest point on the graph of this function if we limit our x value to be between negative 4 and 2? Well, what the extreme value theorem says is that there has to be a highest and a lowest point, but they can only occur at the endpoints. So either at t equals negative 4, t equals 2, or they could occur at the critical values inside the interval. So what we're going to do is make a table. So we're going to make a table of values, right, of function values. So this is the function of the original function, so of function values at each endpoint and at each critical value. So at each endpoint and each critical value. So we're literally just going to plug in this case, these four numbers, the negative 4, 2, negative 2, 1, plug it into my function and see which one corresponds to the largest y value and which one corresponds to the lowest y value, right? So let's make our table. So let's make our t, and then just as a reminder so that we don't have to keep scrolling up, let me rewrite what g of t is. It's 2t cubed plus 3t squared minus 12t plus 4. So let's make a column there. So, and I will list the numbers in order. So our negative 4 is the least, then would come the negative 2, then the positive 1, and then the other endpoint was a positive 2. So let's take our function and evaluate it at these four numbers, right? And then see which one gives us the highest of the high, well, just the highest, the largest function value, and which one gives us the lowest function value. So g of negative 4, 2 times negative 4 cubed plus 3 times negative 4 squared minus 12 times negative 4 plus 4. That turns out to be negative 28. Let's see now, what is g of negative 2? So that's 2 times negative 2 cubed plus 3 times negative 2 squared minus 12 times negative 2 plus 4, and that gives us a positive 24. G of 1. What is g of 1? Well, that one's a little bit easier. That's 2 plus 3 minus 12 plus 4. So that gives us negative 3. And then finally, g of 2. That gives us 2 times 2 cubed plus 3 times 2 squared minus 12 times 2 plus 4, and that gives us see, 8. All right. So there we have it. We have our 4 function values, and then we from this list. So these are essentially the possible locations of the extreme of our absolute min and absolute max. So these are the only possible ones based on the extreme value theorem. And then how do we decide which one is actually the absolute max or which one is the absolute min? Look at these numbers. Look at the negative 28, positive 24, negative 3, and positive 8. And we can see that of these 4 numbers, this is the smallest, right? Because this is negative 28, and this is the largest, right? So this point right here, or I should say this number is the absolute max of this function. It doesn't, I'm sorry, this is the absolute min, not max. This is the absolute minimum of this function. It doesn't get any lower than negative 28 as long as our t is between negative 4 and 2, right? This number here is the absolute max. The function doesn't get any higher than a value of 24, again on the interval from t equals negative 4 to t equals 2. These points here, I don't know what they are, right? But they're not the absolute max. My interest right now is to pick out the highest of the high and the lowest of the low. So again, the table is just a tool, so we have to give a summary of what this table tells us, and this is what we could say. So at t equals negative 4, g of t has an absolute minimum of negative 28. And we could actually put the ordered pair. So negative 4 comma negative 28 is the absolute minimum of this function on this interval. And similarly, we could say at t equals negative 2, g of t has an absolute maximum of 24, right? So again, this is telling you where it occurs, and this is telling you how much is it, what is its value, right? And then this, so at the ordered pair would be negative 2 and then 24, right? And this is all due to this extreme value theorem. It's a really powerful theorem because it guarantees the existence of absolute extrema, these minimum and maximum values that are the lowest of the low and the highest of the high. Not only that, but it tells us exactly where they have to occur, either at endpoints or at critical values inside the interval. And we don't know which is which, so that's why we find all the critical values and then we test. This table is sometimes referred to as a candidates test, right? So this is sometimes called a candidates test, where you've identified the possible values at which the absolute extrema occurs, and then you narrow it down by evaluating your function. So there's a bit of algebra that goes into this, but it starts first with the identification of the critical values, and that's where the calculus comes in and helps us out, right? So that's absolute extrema. The only thing that can change in this process is, again, when you have different types of functions. All right, we'll see you in another video.